Sorry for this. Maybe I should go here. Here we go.
Okay.
Sorry
Great.
for this. And I'm also apologize to all the participants that I did not talk on Wednesday because I was not aware that I'm a speaker in this summer school, but made it possible to speak today. And as you said, it's quite appropriate because we were talking about provenance of silver used for silver coins, and therefore it is good to follow up with the isotope analysis that was already mentioned in the previous talks. Let me also add that this was assembled quite quickly because I only yesterday already in the PDF that will be distributed, you will find some links and maybe some references in addition to this. So let me introduce myself. I'm a scientific director of this institution here, Kurt Engelhorn Center for Archaeometry, which is in Mannheim, and I'm a professor at University of Heidelberg and senior professor at University of Tübingen also. Now, the idea that metals carry some information on their provenance, on the geological provenance, is not new. It's about 200 years old, and we had to wait about 100 years until the ideas that were discussed already in the 19th century were actually to be tested by the analytical methods that had to be developed later on. So it was already discussed in the 19th century that the trace elements are more indicative, but in those days one did not know anything about isotopes. And this is something that I will talk about now. But you see, chemical composition and trace element patterns were used until, let's say, the 1960s or 70s, and the isotope ratios of lead were introduced in the 1970s, and now we have several isotope systems at our disposal, which can be used for provenance studies. But I would say the idea to identify the actual geological source of a metal is, of course, the ultimate goal, but there are intermediate goals that are also interesting. For instance, classifications. Going back to the coins, it would be interesting if different mints, if one mint used different types of silver, for instance, for anyway, because they changed the supplier. And now, this is a summary of a very large study of 22,000 analysis, chemical analysis, that is by atomic emission spectrometry of prehistoric copper objects from Europe and the Mediterranean, some of the Near East. And it turned out that these analyses could be classified, could be differentiated into some 30 different types of copper. And if you look at the distribution of these different copper types in space and time, you find that they are not irregularly distributed. For instance, you have one copper type that we call so-called Falor copper, which with very high concentrations of arsenic and antimony and silver is mainly distributed in Central Europe, up into southern Scandinavia and into the Carpathian Basin. So that is something interesting, was new in those days, but the idea was that where you have the highest density of the distribution, like here in Moravia, there should be the source, the geological source. The problem is we do not have a geological possible source in Moravia, but we have 3 different possible sources at the edges of this major distribution. Anyway, it was very controversially discussed, this study, especially in the Anglo-Saxon literature, with the idea that chemical analysis is of no use to study the provenance of metal objects. Forgive me that this is in German. So we have the history of the isotope application of isotope analysis in archaeometallurgy. from the 1960s until now. And you see that not only lead can be used, or lead isotope ratios, but tin, copper, osmium, nowadays also antimony, silver, and what have you more. It's continuously increasing. So that's a very active field. And now let me, because I was told the audience will be very mixed with some participants not familiar with the basics in the natural sciences. So forgive me for 3 or 4 pictures on the basics. All of you are certainly familiar with the periodic table of the elements. We have some 110 elements on Earth to play around with for provenance studies in principle, but not all of them are routinely analyzed. But usually about a dozen or so, maximum 20 are analyzed in metal objects and tried to relate them to the original geological source. Now, the problem has already been mentioned before, is that on the way from the ore source to the final objects, you have chemical separation processes, you have the smelting of the ore, and maybe also you have some alloying and so on. So that is a problem for the provenance determination based only on the chemical composition or even a trace element pattern. Now, the periodic table of the element contains material that is not homogeneous. Namely, as an example, we all know radiocarbon, carbon-14. That means that the element carbon consists actually of 2 types of carbon atoms, namely, which are called isotopes, being on the same position of the periodic table of the elements. And some other elements consist of more stable isotopes. And the convention is written here, how we write this. And for the use of this additional information, the isotopic information, we use nuclear tables of this type, where we plot the number of neutrons versus the number of protons, which is also gives the name of the element. So this is simply to show you that we have 3,500 nuclides or isotopes of about 110 elements. So we can add an additional parameter for provenance analysis, because the isotope ratio, especially of the heavy elements, let's say from this period on, from rubidium to uranium, does not change on the way from the ore deposit to the final object, because the isotope ratio is fixed by physical processes, actually in the explosion of stars, but it cannot be changed, at least of the heavy elements, cannot be changed by chemical processes, like smelting of the ores. And these are the isotopes, the elements that have radiogenic daughters, that have radioactive isotopes that end up in a stable nucleus, and which alters the isotope ratio of this element with time. So how do we measure this? This is by mass spectrometry, very simple in principle, but very expensive in reality and tedious. You transform your element that you want to determine into ions, and the ions are accelerated and sent through a magnet. And in the magnetic field, they are deflected, and they are deflected according to their mass, so that the isotopes have identical chemical behavior, but they are different physically, and this means that the differentiation, the filtering is by mass. So now this is enough of the basics. What does it mean for lead, which was the first isotope system that was used for the provenance study of metals? Now we have lead is an element that has 4 stable isotopes, namely lead 204, mass 204, 206, 207, and 208. Now, when the Earth was formed, we had an isotope composition as given in these dark columns. But due to the radioactive decay of uranium and thorium, which are also on Earth, but they are radioactive elements, they do not form stable isotopes, but the half-life of these radioactive isotopes is very, very long. It's in the region of billion years. So that over the 4.5 billion years that the Earth is old, the isotope composition of lead on the Earth as a system continuously changed. And this change is induced, can vary in different regions of the Earth, depending on the geological situation where a lead deposit or a copper deposit is formed. So that's the principle, and here you see the variation that has taken place since the formation of the Earth in the usual lead isotope ratio diagram, where 2 ratios are plotted against each other. To find out the full variation of the lead isotope ratios, you would need another diagram because you have 3 independent variables. But anyway, you see that we have a very large variation, although the numbers are small, but these are the measurement precision is very high. We have a variation from here to here, and usually we deal with this system here, or with this part of the diagram. Nevertheless, in this diagram, we also see that we have some geological information. So older ores are on the top right and younger ores on the bottom left. And the principle that we find differences and that we can differentiate ore deposits with lead isotope ratios is the following. In the Earth's mantle, where we have the magma continuously decaying uranium and thorium and continuously altering the lead isotope composition. But when an ore deposit of lead or copper is formed, then the uranium and thorium are separated from lead, and some certain lead isotope ratio is frozen in. It's not changed anymore since when the deposit is formed. And therefore, we can separate different deposits which may have formed in different geological times or in different geological or geochemical situations. The same is true for copper deposits. The problem is that copper deposits do often contain enough lead to have a similar situation, that the lead isotope ratios are frozen in, but very often they have very low lead concentration, and that presents a slight complication. And I will talk about this a little more. Now, you see in the 2 first papers on the application of lead isotope ratios in archaeology. One is by Brill and one is by my good old friend Grögler, who was working in Bern in Switzerland. And he was interested to find out if lead ingots that were found in southern Germany and in Switzerland were actually derived from German ores or from England. And what he at least found was that you can differentiate these different ore mineralized regions with this technique. Now, the technique was then in its infancy, and the precision was very low. Here, for instance, they analyzed only one ore sample from the famous lead-silver deposit of Lorion in Attica. And this is the range of variation that we find nowadays based on some 100 or 120 lead isotope ratios. And this little field comprises all these data, and they can even be differentiated. So the precision has increased dramatically, and this is actually what we need today. Now, one of the first applications was indeed the provenance of silver, because provenance of lead is quite easy, as we have seen. But silver also is associated with lead, because in antiquity, most of the silver was obtained from argentiferous lead ores, like lead galena, but there's also other silver-rich minerals that maybe have been mixed with lead ores. So the result was that indeed what everybody assumed, and what we know from the ancient literature actually, that Athens, the silver coins from Athens were mainly from, or exclusively made from silver from Lorion, and we could distinguish Lorion especially from Sifnos, the island, the Cycladic island of Sifnos, which is also mentioned in the ancient literature, especially by Herodotus, who writes that Sifna was boasting very rich silver mines. So we could also distinguish northern Greek mines like Thasos and Chalkidiki. But the beginning was more optimistic than what we learned later. Here we also learned that the Sifnos did not only deliver silver in the first millennium BC, in the Greek period, but also in the prehistoric periods, especially the early Bronze Age in the 3rd millennium BC. And here you see again, here we have Lorion silver, and here we have Sifnos silver. So we have indirect evidence for the use and the exploitation of the ore deposits on Sifnos, which was a confirmation of Herodotus in a way. And this is simply showing the more detailed view. And you see Sifnos and Lorion can be distinguished very clearly, but many, many other ore deposits in the Aegean, and this is the large field, fall in the similar range of the lead isotope diagram. And here is something that became very clear early. The more diligent we are, the less certain we are, because we have many more overlaps. So we have to use other parameters like the dating of the mines or archaeological reasoning to distinguish this. So we always tend to say the best information the most certain information that we can gain from lead isotope ratios is from where a metal cannot derive. If you do not have a match of lead isotope ratios with the metal, then you can exclude this as a possible source. So then we have here a view that was based on all these new investigations on the development of the metallurgy in the Aegean, because we see a rise of metal objects in the middle of the 3rd millennium in the Aegean, and it was discussed how this came about. It was even discussed if, for instance, the origin of tin bronze may have been in the Northeast Aegean around Troy. Now, the question was then, I will come back to this later. Sorry, I wanted to insert something, a study where we can use lead isotope ratios to actually pinpoint a certain deposit if this certain deposit fulfills a geochemical has certain geochemical parameters. Here we have a study of the site of Arisman, here south of Kashan in central Iran, and the whole plain is filled or covered with slag of the late 4th and early 3rd millennia BC. And we also found there something. Here you see the site itself. We found not only copper slag, which is the majority there, but we found something that was very, very interesting, namely litharge. In the previous talk, it was mentioned that silver is produced from argentiferous lead by the so-called cupellation process, which is simply the oxidation of lead. And then on the oxidation of lead, you form litharge, lead oxide, which does not occur in nature in such large chunks. So this find is definitely proof of silver production from argentiferous lead ores in the 4th millennium BC, actually, where lead and silver appear in the archaeological record. Now the question was, is Arisman, or are the slags in Arisman there because there is a nearby deposit? And the answer was no. We had several students work on deposits around this site, and there were no copper or silver deposits which could be related to the litharge that we found there. But we found a very rich lead-silver deposit in the middle of the Dashti Kefir desert, Nakhlak, which is still in operation today. And what you see here, all these lines worked out veins of lead and silver ore. If you go there indeed, then some of these galleries have fallen down. So we have in the 4th millennium not so many options for the provenance of silver. There have been publications on silver and lead ores in the Taurus region in southern Turkey, and we have also a litharge found in Habuba Kabira, which is in Syria and the Middle Euphrates. And here we have Nakhlak and Arisman, and there is there would be matching isotope ratios in northern Turkey, but this is a very unlikely source region. However, if we look at the Nakhlak ores in detail, then we see a very, very close coincidence of Nakhlak ores with the litharge of Arisman. And here we can not only exclude other sources as possible suppliers, but we can pinpoint Nakhlak because Nakhlak has a very, very small variation of lead isotope ratios in the ores. It is a single stage formation deposit. And therefore, if you have such a small variation, not only in the ores, but also in the litharge that we have found in Arisman, then you can pinpoint it down. And then this means that in the late 4th millennium, it was also already necessary possibly to transport the lead ore, or maybe the lead over 400 kilometers to the west, maybe because there was much more fuel than in the middle of the Dashti Kefir desert. Well, this was lead. Coming back to the Aegean, as I had mentioned, it was quite popular hypothesis in the 1970s to suggest that Troy might be the region where the early tin bronzes emerged, and that gave the rise to the accelerated not only technological but also demographic development in the Aegean in the 3rd millennium. And you see here already the problem that we have. These red points indicate proven and well-known tin deposits or occurrences. The small points indicate only small occurrences. But you see the major tin deposits are in either in Western or Central Europe and in Central Asia, which is Uzbekistan, Tajikistan here, and possibly also in Afghanistan. But there's also tin deposits in Egypt, but none in the vicinity of Troy, and certainly none in the Aegean. Therefore, it was our aim to test the hypothesis that the origin of the tin bronze technology is to be sought in the Troad, in the area around Troy. And here we found the following. The background data had increased very much already. We had ores, which is not all our work, especially Noel and Sophie Gale have worked on copper ores on Cyprus, and we had worked on copper ores from the Troad. And these comprise ores, copper ores, that is, from the Aegean, Bulgaria, and Anatolia all together. And these dark data points are tin bronze objects from Troy itself and the Troad, and it becomes very clear that practically all of them, these cannot derive from copper in the Troad itself. So the copper must come somewhere else. Actually, since we can include the Aegean, Bulgaria, Anatolia, and Cyprus, the whole of Eastern Mediterranean, for these objects, they must come from somewhere. And that's the problem with lead isotope ratios. It's usually easier to conclude where it does not come from than where it comes from. Now the question is, of course, does the tin change, the addition of tin change the lead isotope ratios? The answer is generally no. The tin ores that were used in those times, namely cassiterite, are very low in lead. So, and in addition, the tin is only about 10% of the about composition of tin bronze, so it does not change the isotope composition of the copper. And in addition, we have analyzed this earliest object made of tin, the tin ring from tin bangle from Thermi, and it has also such an outlier isotope composition. So, and since we know that here we have a time information, geological time information, these are lead isotope ratios which indicate a very old geological terrain, which is not to be found neither in the Aegean nor in Anatolia. So we can say it does not come from here, but from somewhere else, which we do not know yet. This is something that I wanted to show first, where we cannot come from. But now I want to provide an example where we can actually identify the provenance of the copper, but not only of the copper, but also of the gold, and possibly also of the tin. And this is this hoard, which was found in 1999, and was unfortunately discovered by grave robbers, I would say, by illicit people who tried to sell this on the antiquities market, the illegal antiquities market anyway. And it came in 2002 to the museum in Halle, where we started an intensive research project on this whole hoard. First of all, let me go back. This object is unique. It's the earliest astronomically correct representation of the night sky. And it is dated, archaeologically dated, from the swords and from the chisels and axes to the middle of the 2nd millennium BC, actually better to 1600 BC, which was later confirmed by radiocarbon dating of one of these swords. But this is itself unique. So therefore, only these objects date this very, very peculiar object, which was incidentally accused as being a fake. So the first question was, of course, do all the parts of the hoard belong together? And that is one of the intermediate goals that I have been talking of. And the answer is yes. We have here 5 trace elements, concentrations plotted against each other, and the star is the sky disk, and the other are the accompanying finds. You see the sky disk in the middle of the accompanying finds, so that you can say this copper comes from the same source. It does not come from the same casting chunk, charge, but because the differences are still too large. But the copper is very, very similar. In the Stuttgart classification, it would be one single type of copper. And here it was possible for us to use this large database of the Stuttgart analysis together with ours. We checked some 30,000 analyses. If we have matching chemical compositions in this database, and we find them, and if we plot them in a geographical way, we find this type of copper is mainly distributed north of the Alpine range into the Carpathian Basin and then into southern Scandinavia. That was already very interesting, very convincing, I would say, but we could even go further, even with the trace element ratios, because in those days we had already analyzed copper ore from Mitterberg. Mitterberg is a copper mine in Austria in the Eastern Alps, and it is one of the earliest investigated prehistoric copper mine. It was already investigated in the 19th century, and it is nowadays estimated that it supplied some 20,000 tons of copper in the entire Bronze Age, Central European Bronze Age. And here you see the dark data points are from the Hoard of Nebra, and the histograms are the composition, reflect the composition of the copper ore. Well, if we can even go further and distinguish within the Mitterberg region several ore districts, which can be differentiated, as you see, and we find that the Nebra hoard fits very well with the main lode of the Mitterberg, which was actually in operation in the 16th century BC, as we know. So this is a very good agreement, and but in those days we were already arguing that the real provenance analysis can only be based on lead isotope ratios, or even better on the combination of trace element patterns and lead isotope ratios. And indeed, what we found here is that we have a very large, a huge variation of lead isotope ratios in the Mitterberg region. Just to give you an idea, one of these symbols, like the blue symbol here, would be the size of the Laurion field that I have shown before. So we have huge variations within one deposit. And if we had not analyzed the Mitterberg ores also isotopically, we would never have thought that these objects, the yellow or brown ones here, the data points from the other neighborhood, that they all are from the same deposit. And here actually, if we had seen only this diagram and before the chemical analysis, we would have said, no, the different parts do not belong together at all. They are all from different mines. And then we find that this type of copper, this is more or less a signifying feature of this copper of the Mitterberg region, namely very homogeneous chemical composition and very variable lead isotope composition. And we have here two other objects, one of which are very similar, actually identical, and one was found in southern Sweden and one was found in eastern Austria, about 900 kilometers apart. And we have analyzed both of them and see the same variation in the lead isotope ratio in the different parts. And so that means that these 10 wheel parts were cast from different batches of metal, and these batches can only have come from the Mitterberg region. Well, this is already, I think, very convincing, but it would be even better if we could exclude other deposits. Here you have a very rough overview of the major copper deposits in Europe. And we have talked about these Eastern Alpine copper deposits. It is not only Mitterberg, but several others, but similar chemical characteristics. But here is the find spot of Nebra, and we have several other relatively rich copper deposits in the vicinity. And the archaeologists were always asking, why would they get copper from the Alps if they have more copper very close by? And the result of a PhD study of Manuela Frotscher showed that we can actually exclude most of the German copper deposits that are closer to the find spot of Nebra. These are the Nebra data. As you see, we can exclude the Kupferschiefer, we can exclude the Thüringer Wald, and many of the other well-known copper deposits in Germany. So that comes to, in the end, to a well-defined provenance of the copper of the Nebra hoard from the Mitterberg region. Now, that you can also go astray shows this example, which was published, I think, in 2014, where copper-based objects, mainly bronzes, were analyzed bronzes from southern Scandinavia were analyzed and were compared with the available database in this research team. And the available database was mainly the Mediterranean. And as I have said before, the more data we have, the more overlap we have. So if you look at all the Mediterranean data, you do find some matching isotope ratios, lead isotope ratios, that is, and then you say, okay, we have copper from Cyprus and from Lorient and from Sardinia and southern Spain in southern Sweden. Well, this overlooks the fact that we have many more copper deposits, very large ones, as I have shown in Mitterberg, in Central Europe, which were not included in this comparison. And therefore, we can now, and it was already known that the types like the sorts that originated probably in the Carpathian Basin where the same types were found in Scandinavia, here in Denmark, and in southern Sweden. And the question was always, was this transferred? Was this transferred directly with the metal produced here? Because Denmark, there is no copper deposit, and so on. Now, recently, we have published together with Helle Vandkilde and Heide Nørgaard a study of 500 southern Scandinavian copper-based objects, and we find a very clear change of the supply routes. We have in the earliest period, the majority of the copper comes from Slovakia, and there's also some input from the British Isles and also from the Eastern Alps, but only a special type of copper, namely Fowler copper. That changes in the century 700 BC, 1600 BC, and we have practically only input from the Slovakian ore mountains, which is replaced almost completely by supply from the Mitterberg region or the Eastern Alps. Some input from the British Isles continues, and it phases out in the late Bronze Age, where now we see a different player coming in, namely the Southern Alps, that's northern Italy, the Trentino, which supplies the bulk of the copper to southern Scandinavia, with some copper also from Slovakia. But we do not find any copper from the Mediterranean delta. So all the clever models that have been developed on this basis are flawed. Well, we have discussed now the provenance of silver, the provenance of lead, and of copper. What about tin? This is a very old question, which was discussed after Schliemann found metal objects that turned out to be bronze in the 1870s in Troy. So this he was already very science-minded. He sent many samples of his finds to Berlin and to all of Europe to have them analyzed. And you see, it says that the early Bronze Age material from Troy, that is 3rd millennium BC, that was already known, does contain tin. So that in those days was the occurrence, the earliest occurrence of tin bronze that we know of. And you see here a publication of 1876 with a nice title, From Where the Tin to the Very Old Bronzes may have come from. Very good question. And here you see suggestions, which is not exhaustive, that have been discussed, some geological possible, some geological not possible. And we do have tin bronzes not only in Troy, like this one here, but in central Anatolia, especially Alachahüyük, this wonderful stag. So we have later found out that this occurrence of early tin bronzes is not confined to Troy, but it goes down to the Gulf, to the Persian Gulf, especially in Mesopotamia. It was also used as a luxury material, as prestigious material. And we still have the problem that the major tin deposits are either in Western Europe, one is in Central Europe, or in Central Asia. So where does the technology originate? Where does the tin come from? And that was a study that we performed within. You have just 5 minutes, I suppose, yes?
Exactly.
Okay. So we have explored the possibility that the tin may have come from Central Asia to these early cultures in Mesopotamia, and we have explored the possibility that the tin may have come to Central Europe from the British Isles. And to cut the story shorter, the provenance of tin is not easy because the trace elements, tin is usually very pure. There are not many trace elements at significant concentrations. And especially if you mix tin with the copper, then the bronze is a minor component in the bronze and only contributes very little to the trace element budget. And in addition, the lead isotope ratios cannot be used in the bronze because the lead isotope ratios are a signature of the copper. Well, let's go over this. And what we've introduced then was the isotope analysis of tin. Tin has no radioactive elements, so actually we would expect that tin has always the same isotope composition all over the world. But if the difference in the mass difference of the tin of some tin isotopes exceeds 10%, then you have some natural processes which induce a fractionation, and that can be used to again identify the ore sources. And this was a first study that we published in 2010, and it turned out that we can differentiate between the most important largest tin deposit in Europe, namely in Cornwall, Southeast England, and the Erzgebirge in Central Europe. And it turned out that the sky disk, the tin in the sky disk, is more compatible with Cornwall and not the Erzgebirge. This came as a surprise to the archaeologists, but when they thought about it, they found it quite attractive. And actually, we also identified the provenance of the gold from Cornwall, which we cannot talk about, especially not in 5 minutes. But what I want to show is that again, the more diligent we are, the less certain we are, because we find. If you look at these, here we plot the database, the newer database of the Erzgebirge and of Cornwall, and you see we have a large overlap in this region. So we cannot say for these, the colored data points are objects, if they come from the Erzgebirge or from Cornwall, but Erzgebirge cannot be excluded. However, for the sky disk, the Cornwall data are much more better match, so that we still keep to the conclusion that the tin in the sky is from Cornwall. There may be Erskine period tin may have been used, but we simply cannot decide. So this is if I have 2 more minutes allowed, and I want to show this, coming back to this question of the swords that were found in Denmark and in Romania, northwest Romania, and also in Nebra. If you now use a 2-component, first of all, we say we find that the lead isotope composition is clearly speaks for a provenance of the copper from the Mitterberg, but where does the tin come from? And you could also see this correlation line as a mixing line, because if you mix, for instance, the composition here with the composition here, all the mixture should lie along a line. Now, if you have a multi-component mixing, then usually the provenance information is lost. But now we have a mixing line if we plot tin isotope ratios and lead isotope ratios. This means we have a mixture of copper and tin, and we have a mixing line. This must mean that these sorts, they were all produced in one workshop, which uses different batches of copper from the Mitterberg and different batches of tin, which varies in this. Therefore, we have a wonderful confirmation of the provenance of these swords from actually most likely, because that's the time question, from northwest Romania. So let me come to the end. We can, of course, use the isotope analysis for other materials like pottery, and it has been done, pottery, glass, pigments, marble, wood, and so on. And to come to a summary, we have now not only lead isotope ratios for lead, silver, tin, and copper. We have osmium isotope ratios, which are very useful for iron, provenance of iron, tin isotope ratio with a potential, copper isotope ratios, not so much for the provenance of the copper, but for the type of the ore deposits that is used, silver isotope ratios similarly, and I would not talk about zinc and iron isotope ratios, but maybe they will come. So thank you very much. Thank you for your patience, and I'm ready for any questions.
Thank you very much, Ernst. It was an enlightening presentation, actually, I should say, as a lover of metals